All right, this is the second part of this problem from chapter 1. It says if the average normal stress in each of the 20 millimeter diameter bars, so same size, is not allowed to exceed 150 megapascals, determine the maximum force P that can be applied to joint C. So we're doing like the same process that we did in the first part, just keeping our axial forces in each member in terms of P, and then we'll see which one kind of has the largest axial force and use that to determine the value of P. So just like before, what color do we want to do? Let's do purple. Just like before, we will do the method of joints. We'll do joint C first. Here's a little joint. This is our Y. This is our X. That'll be the positive directions. Here's P. Again, we don't have a value for P. We're just keeping it uh, as a variable. Draw everything in tension. Just like before, we'll sum the forces in the X direction first. So we got P um, plus, we're going to draw the triangle, 3, 4, 5. Want the 4/5 part, which is it's going to be the horizontal part of um, the force in BC. Oh, why isn't that? All right, and then sorry, just looking at my notes. For some reason I drew a negative there, which doesn't really make sense. But anyway, and now we'll, solve for P. So we'll get that FBC is equal to 1.25 of that value, that P value, and it's in compression, even though we drew it in tension. Now we'll solve the forces in the Y direction. Negative FAC, this will also be negative. Just go ahead and put that right in. And then because it's in compression, it'll be negative, so this will become positive. So then AC, remember AC will be equal to 0.75 P. Do joint B. Like I said before, I like to keep it in tension, and then when I add the value into my equation, I'll make it negative because I'll look up here and be like, oh, there's compression. Instead of having compression, saying compression, and a negative. I just have my own system of not getting confused. So it's good to have your system. Or maybe you're like me and you don't get confused like that. Alright. So we do have the support reaction at that roller, but we don't really care about it because we're just going to get this horizontal axial force in member AB. So sum the forces in the x direction will be equal to 0. Having going to the right be our positive, so FAC will be negative, and then this will also be negative. Um, but then remember that when we add this in, this will become positive. Making AC just equal to 1P. So as we can see, the member BC is kind of going to be our critical member, the one that kind of determines the value of P, as it's the one that has the largest amount. All right. We have the same cross-sectional area as we did before. Again, changing it to meters from millimeters. Right, there's my cross-sectional area, and then um, maximum um, average normal stress is going to be equal to 150, go 10 to the 6 uh, pascals. So we need to use our equation for normal stress. So get me to write a T. For normal stress, use this equation and solve for P. And again, we're going to use the axial loading in member BC. So it's the largest. Doesn't really matter that it's in compression or tension. The magnitude will still be the same, which is what we're looking for. All right, so we'll set these equal to one another, use that also. Sorry, trying to make this video mildly quicker, but somehow maybe not being as quick as I would have wanted. All right, and then we'll solve that for P. Pretty simple stuff. That P is equal to 150 times 10 to the 6 times that cross-sectional area over our proportion of the axial force going to BC. Get an awfully large number, 37.7 kilonewtons.